Tonight, we're going to talk about something so familiar that you probably haven't questioned it in years. Something you feel every moment of your life. It keeps you anchored to the ground, holds the air around our planet, guides the moon in its endless path, and quietly shapes the motion of galaxies billions of light years away. Gravity is always there, invisible, constant, and seemingly obvious. And that's exactly why it's so easy to misunderstand. From the time we're children, we're taught a simple story. Gravity is a force that pulls things downward. You drop an object, it falls. End of explanation. It works well enough for everyday life, so we rarely look deeper. But here's the unsettling idea that changes everything. Gravity is not actually a force in the way you've been taught. Not in the way a magnet pulls iron, or your muscles pull your arm upward. What we call gravity turns out to be something far stranger and far more beautiful than a simple pull. This is where things get uncomfortable, because it means that what we learned wasn't exactly wrong, but it wasn't truly right either. It was a surface-level description, useful but incomplete. And that raises a philosophical question that goes far beyond physics. How many things do we think we understand simply because the approximation works well enough? Think about the Earth. For most of human history, it looked flat. If you stood on the ground, walked for miles, watched ships move across the horizon, everything about your daily experience told you the Earth was flat. And for practical purposes, that belief worked. You could build roads, cities, and empires without ever needing to know the planet was round. But the Earth didn't become spherical when we discovered it. It was always that way. Our understanding changed, not reality. Gravity is much the same. The idea of a downward pull is the flat Earth version of gravity. It matches our intuition, fits our everyday experience, and gets the job done. But it hides a deeper truth about how the universe actually works. A truth that forces us to rethink motion, weight, falling, and even what it means to be standing still. Once you see gravity through this deeper lens, familiar experiences start to feel strange. Falling stops being something that needs an explanation. Standing still does. And the universe begins to look less like a stage where forces push and pull objects around, and more like a dynamic, curved structure that everything moves through naturally. That's the journey we're about to take. Not just to learn a new fact about gravity, but to unlearn an assumption that's been quietly shaping how we see reality itself. Building on that idea, that our everyday understanding of gravity works, but only at the surface, we now step back in time to see how humanity first gave gravity a precise mathematical form. In the late 17th century, Isaac Newton had changed the way we understood motion and the universe with a single unifying idea. In his work, Mathematical Principles of Natural Philosophy, Newton proposed the law of universal gravitation. Every object in the universe attracts every other object, not just planets and stars, but everything. You, the Earth beneath your feet, the moon, distant galaxies, all of them pull on one another. This was a radical claim for its time because it erased the old distinction between the heavens and the Earth. Before Newton, many believed that celestial objects followed divine or special rules, while ordinary matter obeyed different laws. Newton showed that the same mathematics governing a falling apple also governs the motion of the moon and the planets. At the heart of his theory is a simple relationship. The gravitational attraction between two objects increases with their masses and decreases with the square of the distance between them. Double the distance, and the force doesn't merely weaken, it drops to 1/4. Triple the distance, and it falls to 1/9. This inverse square law explains why gravity dominates the cosmos on large scales, but feels so gentle in everyday life. Earth's enormous mass makes its pull unmistakable, while the gravitational attraction between two people standing a meter apart is so weak it's completely undetectable. In fact, gravity is astonishingly feeble compared to other forces of nature. A small refrigerator magnet can easily overcome the gravitational pull of the entire Earth on a paperclip. Electromagnetism, on everyday scales, is roughly 39 orders of magnitude stronger than gravity. That staggering imbalance is one of the deepest unsolved puzzles in modern physics. But Newton's theory captured gravity's behavior with extraordinary accuracy despite this mystery. Using his equations, scientists could predict planetary orbits, calculate trajectories, and understand why the Moon stays bound to Earth. They could explain tides as the result of the Moon's gravity pulling more strongly on the near side of Earth than the far side, stretching the oceans in a slow, rhythmic dance. Newtonian gravity revealed why planets closer to the Sun move faster in their orbits and why distant planets drift more slowly along their vast paths. Its predictive power was so strong that it allowed astronomers to discover objects that had never been seen. In the 19th century, astronomers noticed that Uranus did not follow its expected orbit precisely. Instead of abandoning Newton's laws, they trusted them. By calculating how an unseen planet could perturb Uranus's motion, they predicted where that hidden body should be. When telescopes were pointed to that location, Neptune's substance was found, almost exactly where the mathematics demanded. It was one of the greatest triumphs of theoretical physics, a planet discovered not by observation first, but by equations written decades earlier. For more than 200 years, Newton's law of universal gravitation seemed unassailable. It worked beautifully across the solar system and far beyond. Engineers used it to plan trajectories. Astronomers used it to map the heavens, and its elegance reinforced the idea that gravity truly was a force acting across empty space, instantaneously pulling objects toward one another. Yet even in its golden age, tiny cracks were visible. The most famous involved the planet Mercury. Mercury follows an elliptical orbit around the Sun, but that ellipse slowly rotates over time, a motion known as precession. Newtonian gravity predicts this effect, accounting for the gravitational influence of the other planets. But when astronomers measured Mercury's orbit with increasing precision, they found a small discrepancy. Mercury was precessing slightly more than Newton's equations allowed, about 43 arcseconds per century. It was an incredibly small difference, less than a fraction of a degree over a human lifetime, but it was real. Scientists proposed explanations that stayed within the Newtonian framework. Perhaps there was another unseen planet closer to the Sun, tentatively named Vulcan, whose gravity was tugging on Mercury. Decades of searches found nothing. Others suggested modifying Newton's equations, but those changes disrupted the theory's success elsewhere. The anomaly refused to disappear. At this point in the story, gravity stood in a peculiar position. Newton's theory was overwhelmingly successful, explaining nearly everything we could observe, yet it was not perfect. The law of universal gravitation was like a map that worked everywhere except for one small but stubborn region. Historically, this is often how scientific revolutions begin, not with dramatic failures, but with tiny inconsistencies that refuse to go away. Newtonian gravity provided a powerful, coherent picture of the universe as a system of forces acting between masses across space. It gave us confidence that nature could be described with precise mathematics. But that confidence also hid a deeper assumption. that gravity was fundamentally a force, acting instantaneously, pulling objects toward one another through empty space. The problem with Mercury was not just a technical glitch. It was a hint that this assumption itself might be incomplete. And once that possibility is on the table, the stage is set for a more radical idea. One that doesn't merely adjust Newton's equations, but redefines what gravity is at its core. The small failure in Newton's otherwise magnificent theory did not immediately shatter confidence in classical gravity, but it planted a seed of doubt. That doubt lingered for decades, waiting for someone willing to question not just the equations, but the very idea that gravity was a force at all. In 1915, that person was Albert Einstein. Einstein approached the problem from a radically different direction. Instead of asking how masses pull on one another across space, he asked a more unsettling question. What if gravity isn't something objects do to each other, but something that emerges from the structure of reality itself? His answer became the general theory of relativity, and with it came a complete reimagining of gravity. According to Einstein, gravity is not a force in the traditional sense. It is the curvature of space-time. At first glance, that phrase sounds abstract, even poetic, but it has precise physical meaning. To understand it, we need to rethink two ideas we usually treat as separate: space and time. In everyday life, space feels like a three-dimensional stage where things exist and move. You can go left or right, forward or backward, up or down. Time, by contrast, feels like a separate dimension entirely, flowing relentlessly from past to future. You can't stop it, reverse it, or step sideways out of it. Space is where things happen. Time is when they happen. For centuries, this separation felt natural and obvious. Einstein showed that it is wrong. Space and time are not independent entities. They are fused into a single four-dimensional structure called spacetime. Every event in the universe is not just somewhere or sometime, but somewhere at some time. You cannot fully describe motion, position, or causality without accounting for both together. Even if you're sitting perfectly still in space, you're still moving through time. And when you move through space, you're also moving through time, whether you notice it or not. This unified spacetime is not a passive backdrop. It is dynamic, flexible, and responsive. Mass and energy do not simply exist within spacetime, they shape it. The presence of mass or energy changes the geometry of spacetime, causing it to curve. The more mass or energy concentrated in a region, the more pronounced that curvature becomes. Earth curves spacetime around it. The Sun, being far more massive, produces a much deeper curvature. Even your own body curves spacetime slightly, though the effect is unimaginably small. This curvature is what we experience as gravity. To visualize this idea, physicists often use the rubber sheet analogy. Imagine spacetime as a stretched rubber sheet. Place a heavy bowling ball on the sheet, and it creates a depression. Roll a marble nearby, and instead of traveling in a straight line, the marble curves inward toward the bowling ball. From the marble's perspective, nothing mysterious is happening. It is simply following the straightest path available on the curved surface. The path looks curved only because the surface itself is curved. This analogy captures an important intuition. Objects are not being pulled by an invisible force. They are following paths determined by the geometry they move through. However, the analogy has serious limitations, and it's important not to take it too literally. The rubber sheet is a two-dimensional surface curved into a third dimension by gravity itself, which creates a circular explanation if we're trying to explain gravity. Real spacetime is four-dimensional and does not curve into some higher dimensional space. Its curvature is intrinsic, meaning it is defined entirely within spacetime itself. The analogy is useful as a mental image, but the real physics is deeper and more subtle. In curved spacetime, the notion of a straight line changes. In flat space, the shortest distance between 2 points is a straight line. In curved space, straight lines in the usual sense do not exist. Instead, there are geodesics, the paths that represent the shortest or most natural routes between events in curved spacetime. On the surface of Earth, the shortest path between two cities is not a straight line on a flat map, but a curved arc called a great circle. Airplanes follow these paths not because they are curving intentionally, but because they are the straightest routes on a curved surface. The same principle applies in spacetime. Objects moving under the influence of gravity are not being pulled off straight paths. They are following geodesics through a curved, four-dimensional geometry. This is why planets orbit stars. A planet is not being yanked sideways by a gravitational force. It is moving forward along its geodesic through spacetime curved by the star's mass. From the planet's own perspective, it is traveling in a straight line, doing nothing special at all. The orbit arises because spacetime itself is curved. The planet is in a state of continuous free fall, constantly falling toward the star, but also moving sideways fast enough that it keeps missing it. An orbit is simply perpetual free fall along a curved geodesic. This reinterpretation transforms how we understand weight and motion. Consider astronauts aboard the International Space Station. They appear weightless, floating effortlessly, even though they are only a few hundred kilometers above Earth's surface. Earth's gravitational field at that altitude is still about 90% as strong as it is on the ground. Gravity has not disappeared. The astronauts feel weightless because they, the station, and everything inside it are all falling together. They are following geodesics through Earth's curved spacetime. There is nothing pushing on them to prevent that natural motion, so they float relative to the station. You experience the same effect briefly when you jump. For a fraction of a second, you are in free fall, following your natural geodesic. During that moment, you are weightless, though the sensation is too brief to notice clearly. Extend that fall indefinitely, remove the ground, and the feeling would be identical to what astronauts experience in orbit. Einstein captured this insight in what he called the equivalence principle, one of the central pillars of general relativity. It states that free fall in a gravitational field is locally indistinguishable from floating in deep space, far from any gravitational sources. Imagine you're inside a sealed elevator. If the elevator cable snaps and the elevator begins to fall, you would float inside, just as an astronaut does in orbit. Now imagine the elevator drifting in deep space, far from any stars or planets. You would also float. From inside the elevator, there is no experiment you could perform to tell which situation you are in. Conversely, standing in an elevator at rest on Earth feels identical to standing in a rocket in deep space, accelerating upward at the same rate as Earth's gravity. In both cases, you feel the floor pushing up on your feet. That sensation we call weight is not gravity pulling you down, but the resistance of the floor preventing you from following your natural geodesic. This idea overturns a deeply ingrained intuition. We tend to think that standing still is the natural state, and falling requires an explanation. General relativity reverses this logic. Free fall is the natural state of motion. Standing still on Earth requires a force provided by electromagnetic interactions between your feet and the ground that constantly pushes you upward, away from the geodesic you would otherwise follow. gravity, in this view, is not something acting on you. It is the shape of the spacetime you move through. The equivalence principle also explains why all objects fall at the same rate in a vacuum, regardless of their mass. In Newtonian terms, this required a delicate cancellation between gravitational force and inertia, a coincidence Newton could not explain. In Einstein's framework, there is no coincidence. All objects follow the same geodesics in a given spacetime geometry. Mass does not matter because gravity is not a force acting on mass, it is geometry guiding motion. This geometric view of gravity resolved the mystery of Mercury's orbit naturally. The curvature of spacetime near the Sun is slightly different from what Newton's theory assumes, and that difference produces exactly the observed extra precession. No new planets, no ad hoc corrections, just geometry doing its work. With general relativity, gravity was no longer an invisible hand pulling on matter. It became the architecture of reality itself. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. This simple yet profound relationship replaced the idea of gravitational force with something deeper and more universal. What began as a small discrepancy in a planetary orbit became a doorway into a radically new understanding of space, time, and motion. One that would go on to reshape our view of the entire universe. Once gravity is understood as the geometry of spacetime rather than a force, a series of consequences follows that sound almost impossible at first, yet turn out to be experimentally real. One of the strangest is that time itself does not flow at the same rate everywhere. In strongly curved spacetime, time slows down. Not perceptually, not as an illusion, but physically. Seconds tick at different speeds, depending on where you are and how spacetime is shaped around you. This is not a poetic metaphor. It is a measurable property of reality. In Einstein's picture, time is woven together with space, so when mass curves space, it inevitably affects time as well. The deeper the curvature, the slower time passes relative to regions where spacetime is flatter. Near a massive object like Earth, spacetime is slightly curved, and time runs a little slower than it does far away. Near something extremely dense, like a neutron star or a black hole, the effect becomes dramatic. This idea feels deeply counterintuitive because our daily experience suggests time is universal, flowing the same for everyone everywhere. But general relativity says otherwise, and nature agrees. The first hints came not from exotic cosmic objects, but from experiments much closer to home. In the early 1970s, physicists placed extremely precise atomic clocks aboard commercial aircraft and flew them around the world. Identical clocks were left on the ground for comparison. When the flying clocks returned and were compared with those that stayed on Earth, they disagreed by exactly the amount predicted by general relativity. The clocks on the planes had ticked at slightly different rates because they experienced a different combination of motion and gravitational curvature. The differences were tiny, measured in billionths of a second, but they were unmistakable. Time had not flowed uniformly. It never does. This effect becomes impossible to ignore in modern technology. The Global Positioning System, or GPS, relies on satellites orbiting thousands of kilometers above Earth. These satellites carry atomic clocks that must remain synchronized to within billionths of a second. But because they are higher up, where Earth's spacetime curvature is weaker, their clocks run faster than clocks on the surface. At the same time, their orbital motion causes a smaller, opposing effect that slows them down due to special relativity. If engineers did not correct for both effects, GPS errors would accumulate at a rate of several kilometers per day. Every time you use navigation on your phone, you're depending on Einstein's understanding of time being correct. The system works only because time dilation is real. Gravity does not just shape motion, it shapes the flow of time itself. Another profound consequence of curved spacetime is that light does not travel in straight lines when gravity is present. In Newton's framework, this was puzzling. Light has no mass, so why should gravity affect it at all? In general relativity, the question dissolves. Light always follows geodesics, just like matter. The difference is that light follows special paths called null geodesics, defined by the geometry of spacetime. When spacetime is curved, the straightest possible paths available to light are themselves curved. As a result, light bends when it passes near massive objects. This effect is known as gravitational lensing, and it provided one of the earliest and most dramatic confirmations of Einstein's theory. In 1919, during a total solar eclipse, astronomers had a rare opportunity to test this prediction. Normally, the glare of the sun makes it impossible to see stars near its position in the sky. During an eclipse, however, the sun's light is blocked, allowing background stars to become visible. If Einstein was right, the light from those stars should appear slightly deflected as it passed through the curved spacetime near the sun. The expedition was led by Arthur Eddington, who organized observations from multiple locations around the world. When the photographic plates were analyzed, the stars appeared displaced from their usual positions by exactly the amount Einstein had predicted. The deflection was tiny, less than 2 arcseconds, but it was measurable. With that observation, general relativity leapt from bold theory to experimental reality. Einstein became famous overnight, not because he was charismatic, but because the universe had quietly confirmed that space and time were curved. Today, gravitational lensing is no longer a rare curiosity observed only during eclipses. It is a standard tool in modern astronomy. Massive objects like galaxies and clusters of galaxies curve spacetime so strongly that they can act as cosmic lenses, bending and magnifying the light of more distant objects behind them. Sometimes this produces multiple images of the same galaxy, smeared into arcs or arranged into nearly perfect rings. These shapes are not artistic accidents. They are precise tracings of spacetime curvature on the largest scales. By studying them, astronomers can reconstruct how mass is distributed in the lensing object. This is especially important because much of the universe's mass is invisible. Galaxies do not rotate fast enough to stay intact if only their visible matter were present. Galaxy clusters bend light far more strongly than their stars alone can account for. The only explanation is additional mass that does not emit light at all. We call this dark matter. Gravitational lensing allows scientists to map dark matter directly, not by seeing it, but by observing how it curves spacetime. In effect, gravity becomes a probe, revealing structures that would otherwise remain completely hidden. Light from distant galaxies may take multiple paths around a massive cluster, arriving at Earth at different times. By measuring these time delays, astronomers can infer both the geometry of spacetime and the expansion rate of the universe itself. Once again, gravity is not merely an attractive force, it is the scaffolding through which information travels. Time dilation and gravitational lensing are not exotic side effects that appear only near black holes. They are woven into the everyday operation of the universe. Clocks tick at different rates on mountaintops than they do at sea level. Light curves gently as it passes through Earth's gravitational field, even though the effect is too small for our eyes to notice. On cosmic scales, these same principles shape what we can see and how we measure reality. Together, these effects reinforce a single, unsettling conclusion. Space and time are not rigid, absolute backgrounds against which events unfold. They are dynamic participants. Gravity does not merely move objects through space. It reshapes space and time themselves, altering the flow of moments and the paths of light. What began as an abstract idea about curved spacetime becomes a practical tool, a measurable phenomenon, and a guide to invisible parts of the universe. The deeper we look, the clearer it becomes that understanding gravity means understanding how reality itself is structured. And this realization sets the stage for even more extreme consequences, where curvature becomes so intense that time nearly stops and light can no longer escape at all. As dramatic as time dilation and gravitational lensing may seem, they are still gentle expressions of curved spacetime compared to what happens when gravity reaches its most extreme possible state. If general relativity is pushed to its limits, it predicts objects so dense and so warped in spacetime that our everyday intuitions completely fail. These objects are black holes, and they represent the purest, most uncompromising manifestation of gravity in the universe. A black hole is not simply a very massive object. It is a region of spacetime where curvature becomes so extreme that the usual distinction between space and time begins to collapse. At the heart of every black hole lies a singularity, a point where density becomes infinite and spacetime curvature diverges without bound. Around this singularity is a boundary known as the event horizon. The event horizon is not a physical surface you could touch. It is a geometric boundary in spacetime itself. Once you cross it, all possible paths you can take through spacetime lead inward. Escape is no longer an option, not because something is pulling you back, but because the structure of spacetime gives you no outward direction to move toward. Outside the event horizon, space and time behave in ways that are strange but still familiar. Inside it, the roles of space and time effectively swap. Moving toward the singularity becomes as inevitable as moving forward in time is for you right now. One of the most unsettling consequences of this geometry is what happens to time near a black hole. From the perspective of a distant observer, time near the event horizon slows down dramatically. As an object falls toward a black hole, its clock appears to tick more and more slowly. Light emitted from it becomes increasingly redshifted, stretched to longer and longer wavelengths. To an outside observer, the falling object never quite crosses the event horizon. It appears to freeze just above it, fading away as its light becomes weaker and redder, eventually disappearing from view. But this is only half the story. From the perspective of the falling object itself, nothing so dramatic occurs at the horizon. The fall continues smoothly. Time flows normally, at least initially. The event horizon is not marked by a sudden wall or shock. It is simply the point of no return. This difference in perspectives is not a contradiction. It is a direct consequence of how spacetime is curved. Different observers, following different paths through spacetime, experience time differently. Both descriptions are correct within their own frames of reference. As the fall continues inward, tidal forces become increasingly important. These forces arise because gravity does not pull equally on every part of an object. The side closer to the black hole experiences a stronger curvature than the side farther away. Near Earth, these differences are small. Near a black hole, they become catastrophic. If you were falling feet first toward a black hole, the spacetime curvature at your feet would be far stronger than at your head. The result would be a stretching force that elongates your body. As you fall deeper, this stretching becomes more extreme, while sideways compression squeezes you inward. This process has an uncomfortably vivid name: spaghettification. It is not a metaphor invented for popular science. It is a technical term used by physicists because it describes exactly what happens. Whether spaghettification occurs before or after crossing the event horizon depends on the black hole's mass. For smaller black holes, tidal forces near the horizon are so strong that an object would be torn apart before ever crossing it. For supermassive black holes, whose event horizons can be larger than the orbit of planets, the tidal forces at the horizon can be relatively mild. In such cases, it is theoretically possible to cross the horizon intact, only to be destroyed later as the singularity is approached. Black holes therefore come in very different experiential flavors, all governed by the same equations. Despite their fearsome reputation, black holes are widely misunderstood. One of the most common misconceptions is that they act like cosmic vacuum cleaners, sucking in everything around them. This image is dramatic, but it is wrong. From a distance, a black hole behaves gravitationally just like any other object with the same mass. If our Sun were somehow replaced by a black hole of equal mass, Earth's orbit would remain unchanged. We would continue circling the same location in space. The disaster would come not from being pulled inward, but from the loss of sunlight and heat. Black holes do not actively pull more strongly than stars. Their danger lies in how close you can get to their mass. Because all the mass is compressed inside the event horizon, there is no solid surface to stop you from approaching extremely close to the center, where curvature becomes extreme and tidal forces dominate. This distinction matters because it reinforces the central idea of general relativity. Gravity is not an aggressive force reaching out to grab things. It is geometry. Objects move the way spacetime tells them to move. A black hole is simply a region where spacetime's instructions become absolute and inescapable. For decades, black holes were thought to be truly black, eternal sinks of matter and energy. Once something fell in, it was lost forever. This picture changed in the 1970s, when Stephen Hawking made a discovery that shocked the physics community. By combining principles from quantum mechanics with general relativity, Hawking showed that black holes are not completely black. Quantum physics tells us that empty space is not truly empty. Instead, it seethes with fluctuations where particle-antiparticle pairs briefly pop into existence and annihilate each other. Near the event horizon of a black hole, these quantum fluctuations can be disrupted. One particle may fall into the black hole while the other escapes. To an outside observer, it appears as if the black hole is emitting radiation. This effect is now known as Hawking radiation. The radiation carries energy away from the black hole. Because energy and mass are equivalent, this means the black hole slowly loses mass over time. Given enough time, a black hole will evaporate completely. For stellar mass and supermassive black holes, this process is unimaginably slow. A black hole with the mass of our Sun would take far longer than the current age of the universe to evaporate. But the implication is profound. Black holes are not eternal. They are temporary structures in spacetime, subject to the same laws of thermodynamics as everything else. Hawking radiation also opens the door to one of the deepest puzzles in modern physics: the fate of information. According to quantum mechanics, information cannot be destroyed. According to classical interpretations of black holes, anything that falls in is lost forever. This tension leads to the black hole information paradox, a problem that remains unresolved and sits at the intersection of gravity, quantum mechanics, and the nature of reality itself. Another subtle but important idea related to black holes is the cosmic censorship conjecture proposed by Roger Penrose. It suggests that singularities are always hidden behind event horizons. In other words, nature censors its own infinities. We never see naked singularities exposed to the rest of the universe. If singularities were visible, regions where the laws of physics break down would be observable, and predictability would fail. Cosmic censorship is not a proven law, but it reflects a deep intuition that the universe protects itself from displaying its own mathematical breakdowns. So far, every known singularity appears safely hidden behind an event horizon, but whether this is always true remains an open question. Black holes are therefore not just exotic objects. They are stress tests for our understanding of reality. They push general relativity to its limits and expose where our theories begin to fail. They force us to confront questions about time, causality, information, and the ultimate structure of spacetime. And yet, despite their extremity, black holes are not rare cosmic anomalies. Nearly every large galaxy appears to host a supermassive black hole at its center. These objects influence the formation and evolution of galaxies, shaping cosmic history on the largest scales. The same geometry that governs falling apples and orbiting planets also governs these dark giants. What makes black holes so emotionally powerful is not just their violence or mystery, but what they reveal about the universe. They show that gravity is not a gentle background effect, but a fundamental organizing principle capable of warping reality itself. They demonstrate that time is not universal, that space is not rigid, and that our intuitive ideas about motion and force are approximations that break down under extreme conditions. In black holes, the abstract mathematics of curved spacetime becomes tangible, almost visceral. They are places where equations dictate destiny. To contemplate a black hole is to confront the limits of knowledge and the fragility of intuition. And yet, black holes are not the end of the story. They are gateways to deeper questions, hints that our current understanding, as powerful as it is still incomplete. Gravity, when pushed to its extreme, does not just curve spacetime. It exposes the edges of what we know, inviting us to look beyond, toward a deeper theory that can reconcile geometry with quantum reality. Black holes also force us to rethink something even more basic than motion or time: causality itself. Outside a black hole, cause precedes effect in the way we intuitively expect. Signals propagate outward, information can be exchanged, and events can, in principle, influence distant regions. Inside the event horizon, this logic collapses. Once crossed, the singularity lies not somewhere ahead in space, but ahead in time. No choice, no thrust, no maneuver can alter that future. The singularity is as unavoidable as tomorrow. This is one of the most unsettling implications of general relativity, because it reveals that what we call the future is not merely a direction we move toward psychologically, but a geometric feature of spacetime itself. Near a black hole, geometry dictates destiny. Even light, which normally defines the ultimate speed limit of the universe, cannot escape this fate. Light rays emitted outward inside the horizon still curve inward, dragged along geodesics that all converge toward the singularity. This is why black holes appear black. Not because they absorb light like dark paint, but because spacetime itself tilts so steeply inward that outward paths no longer exist. The darkness of a black hole is not a surface property. It is a statement about the structure of spacetime. This realization transforms black holes from exotic cosmic monsters into profound philosophical objects. They are not just places where things disappear. They are regions where the familiar concepts of space, time, and choice lose their meaning. And yet, despite this apparent finality, black holes are not isolated from the rest of the universe. They interact, merge, spin, and evolve. When two black holes orbit each other, they stir spacetime violently, sending gravitational waves rippling outward at the speed of light. These waves carry information about the masses, spins, and energies involved, allowing distant observers to reconstruct events that happened billions of years ago. In this way, black holes, once thought to be perfectly silent, announce their existence across the cosmos. Their mergers are among the most energetic events since the Big Bang, briefly outshining all the stars in the observable universe combined, not in light, but in the motion of spacetime itself. There is also something deeply counterintuitive about how black holes store information. The entropy of a black hole, a measure of its disorder or information content, is not proportional to its volume, as it would be for ordinary objects. Instead, it is proportional to the area of its event horizon. This suggests that all the information about what has fallen into a black hole may be encoded on its surface, not in its interior. This idea has led to the holographic principle, the notion that a higher dimensional volume of space can be fully described by information stored on a lower dimensional boundary. If true, it implies that the universe itself may be fundamentally holographic, with the reality we experience emerging from deeper, lower dimensional laws. Black holes are the laboratories where these ideas are tested, not with experiments we can perform directly, but with mathematics and observations pushed to their limits. Emotionally, black holes occupy a unique place in human imagination. They represent annihilation, oblivion, and the unknown. But scientifically, they are also engines of order and creation. In the early universe, black holes may have seeded the formation of galaxies, their immense gravity drawing matter together. At the centers of galaxies, supermassive black holes regulate star formation by controlling how gas flows and heats. Far from being purely destructive, they participate in shaping cosmic structure. Gravity, in its most extreme form, becomes both sculptor and destroyer. There is a quiet irony here. The same theory that explains why apples fall and why you feel weight in your legs also predicts objects so strange that time itself collapses inward. General relativity connects the mundane to the monstrous with a single, unbroken set of equations. No special rules are introduced for black holes. They emerge naturally when spacetime is allowed to curve without limit. That elegance is part of what makes them so powerful. Black holes are not exceptions to the laws of physics. They are consequences of those laws taken seriously. And yet, they also expose the incompleteness of our understanding. At the singularity, general relativity predicts infinities, quantities that grow without bound. In physics, infinities are a warning sign. They tell us not that reality is infinite, but that our description has failed. Most physicists believe that a deeper theory, one that unites general relativity with quantum mechanics, will soften or eliminate these singularities, replacing them with something finite and well-defined. What that something is remains unknown. It may involve quantum spacetime, discrete geometry, or entirely new principles we have yet to imagine. Black holes stand at that frontier, marking the boundary between what we understand and what we do not. To contemplate a black hole, then, is to stand at the edge of knowledge. It is to confront a universe that is not obligated to align with human intuition. A universe where time bends, space curves, and the most familiar ideas break under pressure. And yet, It is also to witness the extraordinary power of human reasoning. With nothing more than thought experiments, mathematics, and careful observation, we have inferred the existence of objects from which no light escapes, measured their collisions across billions of light years, and begun to decode the geometry of spacetime itself. Black holes remind us that reality is not only stranger than we imagine, but stranger than we can easily imagine. They are the ultimate expression of gravity's true nature, not as a force pulling things down, but as the architecture of existence itself, capable of folding the universe into shapes that defy common sense. And in their silent darkness, they invite us to keep asking questions, to push further, and to accept that the deepest truths about the universe may always lie just beyond the horizon of what we know. Black holes reveal how violently spacetime can be warped, but they also hint at something even more astonishing. Spacetime does not merely curve in place. It can move. It can ripple. When gravity becomes dynamic, when massive objects accelerate, orbit, or collide, the geometry of spacetime itself can carry disturbances outward across the universe. These disturbances are gravitational waves, and their existence follows naturally from the same geometric picture of gravity that predicts black holes. In general relativity, spacetime is not a rigid stage. It is elastic. Change the distribution of mass and energy, and spacetime responds. When that change happens rapidly and asymmetrically, the response propagates outward as waves, traveling at the speed of light. Albert Einstein predicted gravitational waves in 1916, just a year after completing general relativity. At the time, even he doubted they would ever be detected. The effect was expected to be unimaginably small. After all, gravity is the weakest of the fundamental interactions. If spacetime itself was rippling, the ripples would be subtle beyond belief. For decades, gravitational waves remained a mathematical curiosity, a prediction that seemed forever beyond experimental reach. The first serious hint that they were real came not from a laboratory, but from the sky. In the 1970s, astronomers Russell Hulse and Joseph Taylor discovered a remarkable system. Two neutron stars locked in a tight orbit around each other, known as the Hulse-Taylor binary pulsar. As these dense stars circled one another, they gradually spiraled inward. Their orbital period was shrinking. According to general relativity, this could happen only if the system was losing energy, and the only available channel for that energy loss was gravitational radiation. When Hulse and Taylor calculated how fast the orbit should decay if gravitational waves were being emitted, the numbers matched observation with stunning precision. Over years of careful measurement, the agreement remained exact. It was indirect evidence, but it was compelling. Gravitational waves were no longer just theoretical. They were shaping real astrophysical systems. Hulse and Taylor were awarded the Nobel Prize in 1993, but even then, gravitational waves had not been directly observed. That would require a leap in experimental capability, unlike anything attempted before. Detecting gravitational waves means measuring changes in distance smaller than the diameter of a proton over kilometers-long baselines. It is a level of precision that borders on the absurd. And yet, physicists attempted it anyway. The result was the Laser Interferometer Gravitational Wave Observatory, better known as LIGO. LIGO consists of two massive facilities in the United States, separated by thousands of kilometers. Each detector has two long arms arranged in an L shape, with powerful laser beams bouncing back and forth inside vacuum tubes. If a gravitational wave passes through Earth, it stretches spacetime in one direction and squeezes it in the perpendicular direction. The lengths of the arms change by an infinitesimal amount, altering the interference pattern of the laser light. That change is the signal. On September 14, 2015, LIGO detected its first gravitational wave. The signal was brief, lasting only a fraction of a second, but unmistakable. It came from two black holes, one about 36 times the mass of the Sun, and the other about 29 solar masses, spiraling together and merging more than 1 billion light-years away. As they orbited, they emitted gravitational waves, losing energy and drawing closer. In the final moments, they collided and formed a single black hole. Something extraordinary happened during that merger. The final black hole had a mass of about 62 suns. The missing mass, roughly 3 suns' worth, had not vanished. It had been converted entirely into gravitational wave energy, released in a burst so powerful that for an instant it exceeded the combined light output of all the stars in the observable universe. Not as light, not as particles, but as pure motion of spacetime. This was not just a confirmation of Einstein's equations. It was a new way of observing reality. For the first time, humanity had detected a signal carried not by matter or radiation, but by the geometry of spacetime itself. Since that first detection, LIGO and its international partners have observed dozens of gravitational wave events. Most involve black hole mergers, but some involve neutron stars. In 2017, detectors recorded gravitational waves from the collision of 2 neutron stars. This time, something unprecedented happened. Telescopes around the world detected light from the same event across the electromagnetic spectrum, from gamma rays to radio waves. This marked the birth of multi-messenger astronomy, the study of cosmic events using both gravitational waves and traditional signals like light and particles. The neutron-star merger revealed the origin of heavy elements such as gold and platinum, forged in the extreme conditions of the collision and scattered into space. Gravitational waves provided the dynamics of the event, while light revealed its chemical aftermath. Together, they told a richer story than either could alone. Gravitational wave astronomy is revolutionary not only because it confirms general relativity, but because it opens a new sensory channel on the universe. Light can be absorbed, scattered, or blocked by dust and gas. Gravitational waves pass through matter almost unhindered. They carry information from regions that light cannot escape, such as the interiors of supernovae or the moments just before black holes merge. They allow us to listen to the universe rather than merely see it. And like all new senses, they reveal things we never knew to look for. These observations also test gravity under the most extreme conditions imaginable. The waveforms detected by LIGO match predictions from numerical simulations of Einstein's equations with extraordinary accuracy. Deviations would hint at new physics or alternative theories of gravity. So far, general relativity has passed every test. The speed of gravitational waves matches the speed of light to astonishing precision, ruling out entire classes of modified gravity models. Each detection strengthens confidence in Einstein's theory, while simultaneously probing its limits. Gravitational waves also offer a new way to measure the universe itself. The amplitude of a wave tells us how far away the source is. If we can identify the host galaxy using light, we can also measure how fast that galaxy is receding due to cosmic expansion. This provides an independent method for determining the expansion rate of the universe, potentially resolving tensions between different measurement techniques. In this way, black hole collisions become tools for cosmology. They are standard sirens, announcing their distance through spacetime vibrations alone. The future of gravitational wave astronomy is even more ambitious. Ground-based detectors like LIGO are sensitive to high-frequency waves produced by stellar mass objects. But there are lower-frequency waves generated by supermassive black holes orbiting each other over years or decades that cannot be detected from Earth. To observe these, scientists are planning a space-based observatory called LISA. LISA will consist of 3 spacecraft arranged in a vast triangular formation, millions of kilometers apart, trailing Earth in its orbit around the Sun. Laser beams will link the spacecraft, forming an interferometer the size of a solar system. LISA will detect gravitational waves from sources far beyond the reach of ground-based instruments, supermassive black hole mergers, compact binaries in our galaxy, and possibly relic waves from the early universe itself. These primordial gravitational waves would carry information from the first fractions of a second after the Big Bang, offering a glimpse into energies and conditions impossible to reproduce in any experiment. If detected, they would provide direct evidence for cosmic inflation and shed light on the quantum nature of spacetime. Together, LIGO, its international partners, and future missions like LISA mark a turning point in our relationship with gravity. What began as a subtle correction to Newton's equations has become a dynamic, observable phenomenon. Gravity is no longer just something that shapes orbits and causes objects to fall. It is a medium that can carry signals, encode information, and reveal hidden events across the cosmos. From black holes colliding in distant galaxies to neutron stars forging the elements of life, gravitational waves tell us that space-time is alive with motion. The universe is not silent. It hums, vibrates, and rings. And for the first time, we have learned how to listen. Gravitational waves showed us that space-time can vibrate, carrying information across the universe. But as powerful as that new sense is, it also sharpened an uncomfortable realization. Most of what shapes the cosmos is invisible to us. When astronomers use gravity as their guide, tracking motions, lensing, and cosmic expansion, they consistently run into a profound mismatch between what they see and what gravity demands. Galaxies rotate too fast. Clusters bend light too strongly. The universe expands in a way that defies expectation. Taken together, these clues point to 2 dominant components of reality that we do not directly observe: dark matter and dark energy. They are not minor corrections. They define the universe we live in. Dark matter reveals itself through gravity alone. When astronomers measure how stars orbit within galaxies, they find a paradox. According to Newtonian intuition, stars farther from the galactic center should move more slowly, just as distant planets orbit more leisurely around the Sun. Instead, stars at the edges of galaxies move just as fast as those closer in. If visible matter were all that existed, galaxies should tear themselves apart. The only way to keep them intact is to assume that far more mass is present than we can see. This unseen mass does not emit light, absorb light, or interact electromagnetically in any detectable way. It announces itself only through its gravitational influence. This is dark matter. On cosmic scales, its presence becomes overwhelming. Galaxy clusters, the largest gravitationally bound structures in the universe, bend light far more strongly than their visible matter can explain. Gravitational lensing maps reveal vast halos of unseen mass enveloping clusters and galaxies alike. From these measurements, astronomers conclude that roughly 85% of all matter in the universe is dark matter. Ordinary matter, everything that makes up stars, planets, and people, accounts for only about 15%. We are, quite literally, made of the rarest kind of matter there is. Dark matter plays a crucial role in cosmic history. In the early universe, tiny density variations existed in an otherwise nearly uniform sea of matter and radiation. Dark matter, unaffected by radiation pressure, began to clump first. Its gravity pulled ordinary matter along with it, seeding the formation of galaxies and large-scale structure. Without dark matter, the universe would look radically different. Galaxies might never have formed at all, leaving behind a thin, diffuse fog of particles expanding forever. Dark matter is the scaffolding on which cosmic structure is built. Yet despite its importance, its nature remains unknown. Leading theories suggest it is composed of undiscovered particles that interact weakly with ordinary matter. Massive detectors buried deep underground search for rare collisions between dark matter particles and atomic nuclei. So far, these experiments have found nothing conclusive. Gravity tells us dark matter exists, but it keeps its identity hidden. If dark matter dominates the universe's matter content, dark energy dominates its energy budget. Its discovery was even more surprising. For much of the 20th century, cosmologists assumed that the expansion of the universe, set in motion by the Big Bang, must be slowing down. Gravity pulls matter together, so it seemed inevitable that expansion would decelerate over time. The universe might expand forever, but at an ever-decreasing rate, or perhaps eventually collapse back in a big crunch. In the late 1990s, observations of distant supernovae shattered that expectation. These exploding stars serve as cosmic distance markers. By comparing their intrinsic brightness to how bright they appear, astronomers can determine how far away they are. The results were astonishing. Distant supernovae were dimmer than expected, indicating that the universe's expansion was not slowing down. It was speeding up. Some unknown influence was overpowering gravity on the largest scales, pushing space apart at an accelerating rate. This influence became known as dark energy. Dark energy appears to be a property of space itself. As space expands, more dark energy comes into existence, driving even faster expansion. This creates a runaway effect. Measurements of the cosmic microwave background, large-scale structure, and supernovae all converge on the same conclusion. Dark energy accounts for roughly 68% of the total energy content of the universe. Dark matter contributes about 27%. Ordinary matter makes up the remaining 5%. 95% of the universe consists of substances whose nature we do not understand. That fact alone should inspire humility. The accelerating expansion of the universe has profound implications for its past and future. Looking backward, it reinforces the Big Bang model. If the universe is expanding now, it must have been smaller, denser, and hotter in the past. Extrapolate far enough, and you arrive at a state where all matter and energy were compressed into an extremely hot, dense condition. This was not an explosion in space, but an expansion of space itself. Evidence for this picture is overwhelming. Galaxies are moving away from one another. The universe is filled with a faint glow of microwave radiation, the cosmic microwave background, which is the afterglow of the early universe when it cooled enough for atoms to form and light to travel freely. The abundances of light elements, hydrogen, helium, and traces of lithium match precisely the predictions of nuclear reactions occurring in the first few minutes after the Big Bang. These observations are not isolated facts. They form a coherent narrative of cosmic evolution governed by gravity, expansion, and fundamental physics. The cosmic microwave background also reveals subtle temperature fluctuations, tiny variations in density that later grew into galaxies and clusters under the influence of gravity and dark matter. These patterns encode information about the universe's geometry. On the largest scales, the universe appears remarkably flat. This does not mean it is flat like a sheet of paper, but that the geometry of space is very close to the critical balance between positive and negative curvature. A flat universe can be finite or infinite. It could extend endlessly in all directions, or it could wrap back on itself in a way that has no edges but a finite volume, like the surface of a sphere in higher dimensions. Current observations cannot distinguish definitively between these possibilities. We know the observable universe is finite, limited by the distance light has traveled since the Big Bang, about 93 billion light-years across. Beyond that horizon lies more universe, but its extent remains unknown. Dark energy complicates this picture further. Because expansion is accelerating, distant galaxies are receding from us faster and faster. Eventually, they will cross our cosmic horizon, becoming permanently unobservable. In the far future, observers in our galaxy will see only their local group of galaxies, gravitationally bound together, while the rest of the universe fades from view. The evidence for the Big Bang, cosmic expansion, and dark energy will be inaccessible to them. They may conclude that their island of stars is the entire universe. In this sense, we live at a privileged time in cosmic history when the universe is old enough to be complex but young enough to still reveal its past. Dark matter and dark energy are not just missing pieces in a cosmic puzzle. They redefine what the puzzle is. Gravity, understood as the curvature of spacetime, ties them together. Dark matter shapes structure through its gravitational pull. Dark energy shapes destiny through its influence on spacetime expansion. Together, they determine how the universe evolves on the largest scales. And yet, both remain deeply mysterious. We do not know what dark matter is made of. We do not know why dark energy exists or why its strength has the value it does. These are not small gaps in knowledge. They are central questions about the nature of reality. The universe we can see, the stars, galaxies, and glowing gas, is only a thin veneer on top of a much deeper structure. Gravity has revealed that structure, not by showing it to us directly, but by showing us how the universe moves. Motion, curvature, and expansion have become our most reliable guides to what lies hidden. As with Mercury's orbit and the first hints of curved spacetime, today's anomalies may be signaling another revolution ahead. Dark matter and dark energy could be telling us that our understanding of gravity, successful as it is still incomplete. Or they may point to entirely new forms of matter and energy. Either way, they remind us of a recurring theme in the history of science. The universe is under no obligation to match our expectations. It reveals itself slowly, through patterns that only become clear when we are willing to follow the evidence beyond intuition. Dark matter and dark energy confront us with the possibility that something fundamental is still missing from our picture of gravity. Yet before abandoning or radically revising general relativity, science demands something more disciplined: relentless testing. A theory does not earn its authority by being beautiful or philosophically satisfying. It earns it by surviving every attempt to break it. Few theories in the history of science have been tested as thoroughly and as creatively as Einstein's theory of gravity. Again and again, in environments ranging from Earth's orbit to the hearts of distant galaxies, general relativity has been placed under scrutiny, and so far, it has endured. One of the earliest and most persistent tests involves a problem we encountered long before Einstein entered the story: the strange behavior of Mercury's orbit. Newtonian gravity predicts that a planet's elliptical orbit should slowly rotate over time due to gravitational perturbations from other planets. For Mercury, most of this precession is explained by Newton's laws, but a small residual remained, stubbornly unaccounted for. General relativity resolved this discrepancy naturally. Near the Sun, spacetime is more strongly curved than Newton's theory assumes. Mercury, being closer to the Sun than any other planet, feels this curvature more acutely. When Einstein applied his equations to Mercury's motion, the missing 43 arcseconds per century emerged precisely, without any adjustable parameters. It was not a patch. It was a consequence. This success was historically important because it showed that general relativity did not merely reproduce Newtonian gravity as an approximation. It corrected it where Newton failed. Gravity was no longer an invisible force acting instantaneously across space. It was geometry, and Mercury was tracing a geodesic through curved spacetime. As measurement techniques improved, other relativistic effects predicted by Einstein came within experimental reach. One of these is gravitational redshift. If time flows more slowly in stronger gravitational fields, then light climbing out of those fields should lose energy. Its frequency should decrease, shifting toward the red end of the spectrum. This is not a Doppler effect caused by motion, but a direct consequence of time itself flowing at different rates. The prediction is simple in principle, but extraordinarily subtle to test. On Earth, the difference in gravitational potential between the top and bottom of a building is tiny. And yet, in the late 1950s, physicists performed the Pound-Rebka experiment, measuring the frequency shift of gamma rays over a vertical distance of just 22 meters. The results matched Einstein's predictions. Time was flowing more slowly closer to Earth's surface, and light carried that difference upward. Today, gravitational redshift is no longer a laboratory curiosity. It is a practical reality built into technologies like satellite navigation, where clocks at different altitudes must be corrected for their differing rates of time. Another prediction of general relativity concerns the behavior of spacetime around rotating objects. According to Einstein's equations, mass does not merely curve spacetime. When it spins, it drags spacetime along with it. This effect is known as frame dragging. Imagine spacetime as a viscous fluid. A spinning object stirs it, twisting nearby geodesics. The effect is vanishingly small for everyday objects, but measurable around massive, rapidly rotating bodies like Earth. To test this prediction, NASA launched Gravity Probe Bs in 2004. The mission carried 4 ultra-precise gyroscopes into orbit around Earth. If spacetime were not being dragged, the gyroscope's axes would remain fixed relative to distant stars. If frame dragging existed, their orientations would slowly drift over time. Measuring this drift required extraordinary precision. The gyroscopes were among the most perfect spheres ever manufactured, polished to within a few atomic layers of perfection. Over the course of the mission, Gravity Probe B measured 2 relativistic effects: the geodetic effect, caused by Earth's mass-warping spacetime, and frame dragging, caused by Earth's rotation. After years of data analysis, the results matched general relativity's predictions within experimental uncertainty. Spacetime around Earth was indeed being twisted by its rotation. The effect was small, amounting to mere milliarc seconds per year, but it was real. Earth was dragging spacetime along with it as it spun. While Earth provides a relatively gentle testing ground, nature offers far more extreme laboratories. Binary pulsars are among the most powerful. Pulsars are rapidly rotating neutron stars, the ultra-dense remnants of massive stars that collapsed under gravity. A neutron star packs more mass than the Sun into a sphere only about 20 kilometers across. Its gravity is intense, and its rotation produces beams of radio waves that sweep across space like lighthouse beams. When a pulsar is part of a binary system, orbiting another neutron star or pulsar, it becomes an exquisite probe of relativistic gravity. The timing of pulsar signals is extraordinarily regular. Some pulsars rival atomic clocks in their precision. By tracking the arrival times of these pulses, astronomers can measure orbital dynamics with incredible accuracy. In binary pulsar systems, general relativity predicts a host of effects: orbital decay due to gravitational wave emission, time dilation caused by strong gravitational fields, and relativistic precession of the orbit itself. The Hulse-Taylor pulsar provided the first indirect evidence for gravitational waves, but many other systems have since been discovered, each offering new tests. In some binaries, the stars orbit each other in just a few hours. Their gravitational interaction is so strong that relativistic effects dominate the system's behavior. Observations consistently match Einstein's predictions. No deviations have been found. In these systems, gravity operates in a regime far beyond anything accessible in the solar system, yet general relativity remains intact. One of the most visually striking tests of general relativity comes from observing black holes directly. For decades, black holes were inferred indirectly through their effects on nearby matter. That changed in 2019 when the Event Horizon Telescope collaboration released the first image of a black hole's shadow. This black hole, located at the center of the galaxy, Messier 87, has a mass billions of times that of the Sun. The image did not show the black hole itself, which emits no light, but the glowing ring of hot gas swirling around its event horizon. The dark center is the shadow cast by the black hole against this background, shaped by extreme gravitational lensing. Light from the accretion disk is bent around the black hole, producing a ring whose size and shape can be predicted precisely by general relativity. When the image was compared with simulations based on Einstein's equations, the match was remarkable. The observed shadow had exactly the size expected for a black hole of that mass. There was no room for exotic alternatives or major deviations from general relativity. In 2022, the Event Horizon Telescope achieved an even more challenging feat: imaging the black hole at the center of our own galaxy. Milky Way. Known as Sagittarius A, this black hole is smaller and more dynamic than the one in Messier 87. Its surrounding gas changes rapidly, making imaging far more difficult. And yet, the resulting image once again matched the predictions of general relativity. The shadow's size and shape were consistent with a rotating black hole described by Einstein's equations. These images are more than scientific triumphs. They are visual confirmations of an idea that once seemed almost metaphysical: that gravity is geometry. We are seeing the imprint of curved spacetime itself. Light is tracing paths dictated by the geometry around an object from which it cannot escape. The images do not merely illustrate theory, they test it. Any significant deviation in the shadow's shape would have signaled new physics. None was found. Even closer to home, general relativity continues to be tested in subtle ways. Atomic clocks placed at different altitudes tick at different rates, exactly as predicted. Signals sent between spacecraft experience time delays as they pass near massive bodies, an effect known as the Shapiro delay. Radio waves sent past the Sun take slightly longer to reach their destination because spacetime is curved in the Sun's vicinity. Measurements of this effect using spacecraft signals have confirmed general relativity to high precision. Each of these tests probes a different aspect of the theory. Some examine how spacetime curves around mass. Others test how time flows in gravitational fields. Others still investigate how space-time responds to motion and rotation. Taken together, they form an interconnected web of evidence. No single experiment stands alone. They reinforce one another, painting a consistent picture across vastly different scales and environments. This is why general relativity remains the foundation of modern gravitational physics. It is not because it answers every question. Dark matter and dark energy remain unexplained. Singularities signal breakdowns in our understanding. Quantum gravity lies beyond its reach, but within its domain, general relativity has proven extraordinarily resilient. Every time it has been tested, from the slow precession of Mercury's orbit to the violent mergers of black holes, it has delivered correct predictions. This resilience has an important implication. Whatever new theory eventually replaces or extends general relativity must reproduce all of these successes. It cannot simply discard Einstein's framework. It must contain it as an approximation, just as general relativity contains Newtonian gravity. The bar for a new theory is set extraordinarily high. In this sense, the tests of general relativity are not just confirmations of a century-old idea. They are constraints on the future. They define the landscape in which new physics must live. Gravity Probe B, binary pulsars, gravitational redshift experiments, and black hole images are not isolated achievements. They are milestones marking how far we have pushed our understanding of gravity and how far it still holds. Each test deepens our confidence while sharpening the mystery. Gravity works exactly as Einstein predicted, even where it seems most likely to fail. And that, paradoxically, is what makes the unanswered questions about dark matter, dark energy, and quantum gravity so compelling. The theory that should have broken did not. The universe continues to follow Einstein's geometry with uncanny fidelity. And so we are left with a profound tension, a theory that works spectacularly well, and a cosmos that is still largely unknown. That tension, between extraordinary success and profound incompleteness, is what gives the tests of general relativity their deeper meaning. They are not victory laps. They are stress tests that reveal both the strength and the boundaries of the theory. Every confirmation tightens the constraints on how gravity can behave, leaving less room for speculation and more pressure on whatever comes next. In this sense, each successful test is not a closing of the book, but a narrowing of the path forward. Consider how these tests span such radically different regimes. Mercury's orbit probes gravity in a relatively weak field, where space-time curvature is gentle and velocities are modest. Frame. Dragging around Earth tests. Gravity in the presence of rotation, where space-time itself is subtly twisted. Binary pulsars push gravity into a strong field, high-velocity regime, where objects move at significant fractions of the speed of light. Black hole imaging probes the very edge of space-time structure, where curvature becomes extreme and intuition fails completely. That a single theory connects all of these domains is astonishing. It suggests that gravity is not a patchwork of rules tailored to different situations, but a unified principle woven into the fabric of reality. At the same time, the precision of modern tests exposes how fragile our understanding could be. Many proposed alternatives to general relativity attempt to explain dark matter or dark energy by modifying gravity itself. Some introduce new fields. Others alter how space-time responds to mass on large scales. But these ideas face a formidable obstacle. They must reproduce every successful test of general relativity to exquisite accuracy. A theory that explains galaxy rotation curves but fails to predict the correct shadow of a black hole or the precise timing of a binary pulsar, is not an improvement. It is a step backward. Gravity, it turns out, is not easily fooled. Even small deviations from Einstein's equations tend to produce observable consequences that conflict with data. This is why general relativity, despite its known limitations, remains central. It has not been protected from criticism. It has been assaulted from every direction imaginable, and it continues to stand. There is also an important philosophical lesson embedded in these tests. General relativity teaches us that many effects we once thought of as separate, force, motion, time, and geometry, are deeply intertwined. When we test gravity, we are not just testing how objects fall or orbit. We are testing how clocks tick, how light travels, and how information moves through the universe. A failed test would not merely require adjusting an equation. It would force a rethinking of how space and time themselves behave. This is why precision matters so much. Tiny discrepancies can signal profound shifts in understanding. Historically, revolutions in physics have often begun with small anomalies. Mercury's extra precession was tiny, yet it reshaped gravity. The ultraviolet catastrophe was a technical problem, yet it led to quantum mechanics. Today, the anomalies associated with dark matter and dark energy may be playing a similar role. But unlike in Newton's time, we now have a theory that has been tested to extraordinary precision. Any future revolution will have to be subtle, building on general relativity rather than overthrowing it outright. The images from the Event Horizon Telescope capture this duality perfectly. On one hand, they are triumphs of human ingenuity, achieved by linking radio telescopes across the planet to form an Earth-sized instrument. On the other hand, they are stark reminders of how little we truly understand. We can see the shadow of a black hole, but we cannot say what happens at its core. We can predict the shape of the shadow with confidence, but not the ultimate fate of information that falls inside. The same equations that succeed so spectacularly at the horizon fail completely at the singularity. General relativity guides us to the edge of knowledge, then falls silent. Even so, the cumulative weight of evidence has transformed gravity from an abstract concept into a directly observed phenomenon. We have seen spacetime curve light, slow time, drag inertial frames, radiate energy, and cast shadows. These are not metaphors. They are measurements. The universe has repeatedly answered our questions about gravity, and it has answered them in Einstein's language. That fact carries emotional as well as scientific weight. It means that the strange, counterintuitive ideas of curved spacetime are not philosophical speculation. They describe the world we inhabit. And yet, the very success of general relativity sharpens the mystery of what lies beyond it. Dark matter and dark energy dominate the cosmos, but they fit awkwardly into the framework. Singularities mark places where the theory breaks down. Quantum mechanics, our other great pillar of physics, refuses to merge smoothly with Einstein's geometry. These tensions suggest that gravity, as we currently understand it, is part of a larger story. A story that we have only begun to glimpse. The tests of general relativity therefore serve a dual purpose. They reassure us that we are on solid ground, that our descriptions of gravity are not illusions or convenient fictions. At the same time, they warn us that this ground has edges. Beyond them lies territory where new ideas are required. Gravity has proven to be both deeply reliable and deeply mysterious. It governs the fall of an apple and the collision of black holes with the same mathematical grace, yet it leaves most of the universe's substance unexplained. This is not a failure of science. It is its engine. Each confirmation of general relativity is a reminder that nature follows rules, even when those rules defy intuition. Each unanswered question is an invitation to look deeper. As we push gravity to ever more extreme regimes and measure it with ever greater precision, we are not just testing a theory. We are mapping the limits of human understanding itself. Every successful test of general relativity strengthens our confidence in its description of gravity. And yet, that very success sharpens a contradiction at the heart of modern physics. The deeper we probe gravity, the more clearly we see that our two greatest theories of nature, general relativity and quantum mechanics, do not speak the same language. Each is astonishingly accurate within its own domain. Each has been tested to extremes. But when gravity and quantum effects are forced to coexist, the theories collide. This is not a philosophical discomfort. It is a mathematical and conceptual breakdown that signals the limits of our current understanding. General relativity describes gravity as the smooth curvature of spacetime, a continuous geometric structure. Quantum mechanics, by contrast, describes reality as fundamentally discrete and probabilistic, governed by uncertainty and quantized interactions. In the quantum world, fields fluctuate, particles pop in and out of existence, and outcomes are described by probabilities rather than certainties. Time in quantum mechanics is an external parameter, something that ticks uniformly in the background. In general relativity, time is dynamical, stretching and slowing depending on gravity and motion. These views are not merely different. They are incompatible at a deep level. Try to apply quantum rules to spacetime itself, and the mathematics breaks down. Try to describe gravity as a quantum force like the others, and infinities appear everywhere. This conflict becomes unavoidable in extreme environments, especially inside black holes and at the beginning of the universe. Nowhere is the tension more vivid than in the black hole information paradox. According to quantum mechanics, information about a physical system, its complete quantum state, cannot be destroyed. It can be scrambled, hidden, or transformed, but never erased. This principle underlies everything from atomic physics to quantum computing. General relativity, on the other hand, seems to allow information to disappear behind an event horizon, never to return. If a black hole evaporates completely through Hawking radiation, as theory suggests, what happens to the information about everything that fell in? If it is lost, quantum mechanics is violated. If it is preserved, general relativity's classical picture of black holes is incomplete. This paradox is not a technical curiosity. It strikes at the core of what physical laws are allowed to do. Over decades, physicists have proposed many resolutions. Perhaps information escapes encoded subtly in Hawking radiation. Perhaps it is stored on the event horizon itself. Perhaps black holes leave behind stable remnants. Each idea challenges intuition and forces revisions to existing frameworks. What is clear is that the paradox cannot be resolved without a theory that unites gravity and quantum mechanics into a single coherent structure. This need has driven the search for quantum gravity, a theory that would describe spacetime itself as a quantum object. One approach to this problem is string theory. In this framework, the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. Different vibrational modes correspond to different particles. Remarkably, when string theory is formulated consistently, gravity appears automatically. One of the vibrational modes of the string behaves exactly like a quantum version of the graviton, the hypothetical particle that would mediate gravitational interactions. This is not an add-on. It is a built-in feature. String theory suggests that gravity is not just compatible with quantum mechanics, but emerges naturally from it when the underlying structure is extended and non-point-like. However, this elegance comes at a cost. String theory requires additional dimensions of space beyond the 3 we experience, typically 6 or 7 extra dimensions curled up at scales far too small to detect. It also predicts a vast landscape of possible solutions, each corresponding to a different universe with different physical laws. This makes it extraordinarily difficult to extract unique, testable predictions. String theory offers a mathematically rich framework that resolves many conceptual problems, including aspects of the black hole information paradox, but it remains experimentally unverified. Another major approach is loop quantum gravity. Rather than introducing new fundamental objects like strings, loop quantum gravity attempts to quantize spacetime itself directly. In this view, space is not continuous. It is composed of discrete, indivisible units, woven together in a network known as a spin network. Areas and volumes come in quantized chunks, much like energy levels in an atom. Time evolution becomes a process of these networks changing and reconnecting. In loop quantum gravity, spacetime has an atomic structure. This approach preserves the geometric insight of general relativity while incorporating quantum discreteness. It suggests that singularities, where classical curvature becomes infinite, may be replaced by finite, quantum-regulated structures. For example, the Big Bang might be replaced by a Big Bounce, where a previous contracting universe rebounds into expansion. Similarly, black hole singularities might be resolved into regions where spacetime transitions rather than ends. Loop quantum gravity has made progress in describing quantum geometry, but like string theory, it faces formidable challenges. Connecting its abstract mathematical structures to observable physics remains difficult. The theory is still incomplete, and experimental tests are elusive. Both string theory and loop quantum gravity, despite their differences, converge on a radical idea. Spacetime is not fundamental. It emerges from deeper, more basic degrees of freedom. This notion finds its most striking expression in the holographic principle. Inspired by black hole thermodynamics, the holographic principle proposes that all the information contained within a volume of space can be described by information encoded on its boundary. In this view, the universe is like a hologram, a three-dimensional reality emerging from two-dimensional data. The holographic principle is not merely philosophical. In certain idealized settings, it has been realized mathematically with stunning precision. In these cases, a theory of gravity in a higher dimensional spacetime is exactly equivalent to a quantum field theory without gravity defined on its boundary. This duality suggests that gravity itself may be an emergent phenomenon, arising from quantum entanglement and information relationships rather than being fundamental. If true, this would explain why gravity is so weak compared to other forces. It would not be a force in the usual sense, but a large-scale manifestation of deeper quantum processes. Black holes, once again, play a central role in this picture. Their entropy scaling with surface area rather than volume hinted at holography long before the idea was formalized. From this perspective, the event horizon is not just a boundary of no return. It is a storage device for information, encoding everything that has fallen in. The interior of the black hole, with its apparent paradoxes, may be a redundant description. The true degrees of freedom could live on the horizon itself. This idea challenges our most basic intuitions about space and locality. It suggests that what we perceive as volume may be an emergent illusion, with the true physics happening on lower dimensional structures. Despite these profound insights, quantum gravity remains frustratingly out of reach experimentally. The scales at which quantum gravitational effects become significant are defined by the Planck scale. At this scale, lengths are on the order of 10 to the minus 35 meters. Times are unimaginably brief, and energies are far beyond what any current or foreseeable experiment can achieve. To probe spacetime directly at the Planck scale would require energies comparable to those present shortly after the Big Bang. Particle accelerators, powerful as they are, fall many orders of magnitude short. This creates a unique challenge. Unlike other areas of physics, quantum gravity cannot be tested by simply building a bigger machine. Physicists must rely on indirect clues. They look for tiny deviations from known laws, subtle imprints in cosmological data, or unexpected behavior in extreme astrophysical environments. Gravitational waves may carry hints of quantum structure if observed with enough precision. Black hole evaporation, if ever detected, could reveal how information is preserved. The early universe, through the cosmic microwave background, may encode signatures of quantum spacetime. But these are faint signals, buried beneath layers of complexity. The difficulty of experimentation does not diminish the importance of the problem. On the contrary, it elevates it. Quantum gravity is not a niche topic. It sits at the intersection of our deepest questions about reality. What is space made of? What is time? Is the universe fundamentally continuous or discrete? Are the laws of physics fixed, or do they emerge from deeper principles? These are not idle speculations. They determine what kinds of explanations are possible. They shape our understanding of causality, information, and existence itself. There is also a psychological challenge embedded in this pursuit. For centuries, physics advanced by extending intuition from everyday experience. Quantum mechanics forced us to abandon classical pictures of particles and waves. General relativity forced us to abandon absolute space and time. Quantum gravity may demand an even more radical shift, one that abandons spacetime itself as a fundamental concept. That is not easy. Human cognition evolved to navigate a world of solid objects and linear time, not a universe built from entanglement and geometry. The struggle to unify gravity and quantum mechanics is therefore not just technical, it is cognitive. We may lack the right metaphors, the right intuitions, and perhaps even the right mathematical language. And yet, progress continues. New ideas emerge, old ones are refined, and unexpected connections appear. Techniques developed in one area find applications in others. Insights from black holes influence quantum information theory. Concepts from entanglement reshape our understanding of spacetime. The boundaries between disciplines blur. This is often how breakthroughs happen, not through a single decisive experiment, but through a gradual convergence of ideas. To stand at the frontier of quantum gravity is to accept uncertainty as a permanent companion. We know where our theories work, and we know where they fail. Between those regions lies a vast territory of ignorance. But this ignorance is not empty. It is structured by constraints, guided by consistency, and illuminated by partial successes. General relativity tells us how spacetime behaves on large scales. Quantum mechanics tells us how matter and energy behave on small scales. Quantum gravity must honor both, and in doing so, it may reveal that both are approximations of something deeper. This is the boundary of modern understanding. It is a place where confidence gives way to curiosity, and where answers generate more questions. Gravity, once thought to be the simplest of forces, has led us here, to the edge of explanation. In trying to understand why things fall, we have been forced to confront the nature of time, space, and information. We have learned that reality is layered, and that each layer hides another beneath it. Whether quantum gravity ultimately takes the form of strings, loops, holograms, or something entirely unforeseen, one thing is clear: it will change how we think about the universe at the most fundamental level. And in that sense, the search itself is already a profound discovery. At this frontier, even the meaning of evidence becomes ambiguous. In most areas of physics, progress is driven by experiments that decisively rule ideas in or out. Quantum gravity resists that pattern. The signals we hope to detect are subtle distortions layered on top of well-understood phenomena. A tiny deviation in a gravitational wave's phase, an unexpected correlation in the cosmic microwave background, a faint imprint in black hole radiation. These are the kinds of clues researchers search for. None would shout. All would whisper. Interpreting them requires extraordinary care because the risk of mistaking noise for new physics is always present. And yet, history suggests that nature often reveals her deepest secrets quietly, not with explosions, but with inconsistencies that refuse to disappear. One promising direction comes from the growing connection between gravity and quantum information. Over the last 2 decades, physicists have discovered that concepts originally developed to understand entanglement, error correction, and information flow also appear in the mathematics of spacetime. In some formulations, the geometry of space emerges from patterns of quantum entanglement. Change the entanglement structure, and space itself reshapes. In this view, spacetime is not a stage on which quantum systems act. It is a byproduct of how those systems are connected. Distance, curvature, and even gravity may reflect the structure of information rather than something fundamentally geometric. This idea reframes the old question of what spacetime is made of. It may not be made of anything in the traditional sense. It may be an emergent concept, like temperature, which arises from the collective behavior of microscopic particles, but is not meaningful at the level of individual atoms. If spacetime is emergent, then trying to quantize it directly may be like trying to quantize a wave in a crowd without acknowledging the people beneath it. This perspective also sheds new light on the black hole information paradox. If information is fundamentally preserved and encoded in correlations, then black holes may not destroy information at all. They may scramble it in ways that are extraordinarily complex but ultimately reversible in principle. From this angle, the event horizon becomes less like a one-way wall and more like a processing boundary, redistributing information into forms that are nearly impossible to reconstruct but not fundamentally lost. The paradox then reflects not a failure of physical law, but a failure of classical intuition. We expect information to be localized, accessible, and traceable. Quantum gravity suggests it may be delocalized, hidden in global correlations that span spacetime itself. There is also growing interest in the possibility that gravity is not fundamental at all. In some speculative frameworks, gravity emerges as an entropic force, arising from statistical tendencies of microscopic degrees of freedom. Just as pressure emerges from the collective motion of molecules, gravity might emerge from the tendency of quantum systems to maximize entropy. In this picture, Einstein's equations resemble thermodynamic laws rather than fundamental dynamical rules. They describe equilibrium conditions, not microscopic mechanisms. If this is true, then searching for the graviton may be misguided. Gravity would not be mediated by particles in the usual sense. It would be a macroscopic phenomenon, arising inevitably from deeper statistical principles. This idea is controversial and far from settled, but it illustrates how radically our understanding may need to shift. The Planck scale looms over all of these discussions as both a guide and a barrier. It marks the scale at which quantum fluctuations of spacetime become unavoidable. Below this scale, the smooth geometry of general relativity dissolves into something granular or foamy. But the Planck scale is so remote from experimental access that it forces physics into a new mode of reasoning. Instead of direct tests, theorists rely on consistency, mathematical coherence, and the requirement that new ideas reproduce known physics in appropriate limits. This is a more constrained and abstract approach, but it is not without precedent. The existence of atoms was inferred long before they could be directly observed. The structure of spacetime may be inferred in a similar way, through its effects rather than its substance. Cosmology offers one of the few windows where quantum gravity might leave observable traces. The earliest moments of the universe were governed by energies close to the Planck scale. If quantum gravitational effects influenced cosmic inflation or the initial conditions of expansion, they may have left imprints in the large-scale structure of the universe or in subtle patterns of the cosmic microwave background. These signals are faint and difficult to disentangle from other processes, but they represent one of the best hopes for empirical guidance. In this sense, the universe itself becomes the experiment, unfolding over billions of years and offering clues to those patient enough to decode them. What makes this pursuit uniquely challenging is that it asks us to give up the comfort of a final picture. Quantum gravity may not deliver a single clean image of reality. It may reveal that reality admits multiple complementary descriptions, each valid in its own domain. Spacetime may be real in one context and emergent in another. Causality may be fundamental in some regimes and approximate in others. This is deeply unsettling to a mind trained to seek definitive answers, but it may also be a more honest reflection of how nature works. At the boundary of knowledge, simplicity often gives way to subtlety. And yet, there is something profoundly human in this struggle. The quest for quantum gravity is driven not only by technical necessity, but by a desire for coherence. We want a universe that makes sense as a whole, not one stitched together from incompatible pieces. We want to know whether the laws governing the smallest scales and the largest structures are expressions of a single underlying principle. Gravity has led us to ask these questions by refusing to fit neatly into our existing frameworks. It has forced us to confront the possibility that space and time, which feel so fundamental, may themselves be emergent concepts. This is not the end of the story, but a pause at its edge. Beyond this point lie ideas that are still forming, theories that are incomplete, and questions that may take generations to answer. But standing here, at the boundary of modern understanding, we can see the shape of the problem clearly. Gravity connects everything, from the fall of an apple to the birth of the universe. In trying to understand it fully, we have been pushed to reconsider the deepest assumptions about reality itself. Whatever quantum gravity turns out to be, it will not just refine our equations. It will change how we think about existence, causality, and the meaning of physical law. And in that sense, the search for it is already transforming our understanding, even before the final answer comes into view. After confronting the limits of our theories at the Planck scale, it is tempting to think of gravity as something abstract, remote, or inaccessible. But gravity does not belong only to black holes and quantum paradoxes. It is the same principle that shapes the ground beneath your feet, the air you breathe, and the sky above your head. One of the quiet lessons of modern physics is that gravity does not change its identity as we move across scales. What changes is how its influence unfolds. From the interior of Earth to the vast cosmic web of galaxies, gravity acts as a continuous thread, linking the intimate to the immense. Seen this way, gravity is not just a force or a curvature. It is a storyteller, shaping structures across time and scale. On Earth, gravity is so familiar that it disappears into the background of experience. Yet nearly every feature of our planet depends on it. Earth's atmosphere exists because gravity holds it in place. Without sufficient gravitational pull, gases would escape into space, as they largely have on smaller worlds. The thickness of the atmosphere, its pressure at the surface, and the way it circulates are all determined by gravity, working in concert with temperature and rotation. The balance between gravitational pull and thermal motion sets the boundary between air and vacuum. Gravity also governs the oceans. It pulls water into a roughly spherical shape, creating sea level and enabling tides when combined with the gravitational influence of nearby bodies. Even the gentle rise and fall of the sea along coastlines is a reminder that gravity is never acting alone, but always in relationship with other masses. Beneath the surface, gravity plays an even deeper role. Earth's interior is layered because gravity pulled denser materials inward during the planet's formation. Heavy elements like iron sank toward the center, forming the core, while lighter materials rose toward the surface. This gravitational differentiation created the structure that makes Earth geologically active. The molten outer core generates a magnetic field that shields the planet from harmful radiation. Tectonic plates move because gravity and internal heat drive convection in the mantle. Mountains rise and erode under gravity's influence, cycling material between crust and interior. Over geological time, gravity shapes continents, sculpts landscapes, and regulates the long-term stability of the planet. None of this feels dramatic, yet without gravity's steady guidance, Earth would be a radically different place, likely hostile to life as we know it. Moving outward, gravity organizes the solar system into a dynamic but remarkably stable architecture. Planets follow nearly flat, orderly orbits not by accident, but because gravity naturally smooths chaotic motion over time. Interactions between orbiting bodies lead to resonances, subtle gravitational rhythms that lock objects into repeating patterns. Some moons orbit in precise ratios, tugging on one another in a gravitational dance that can last billions of years. Rings around planets form when gravity balances cohesion and tidal forces, preventing material from clumping into a single body. These rings are not static decorations. They are active systems shaped by countless gravitational interactions. Comets, originating from distant reservoirs of icy debris, follow long, looping paths dictated by gravity alone. Occasionally, they are nudged inward, plunging toward the inner system, where heat transforms them into glowing visitors with streaming tails. Each trajectory is a solution to the same gravitational equations that govern falling apples and orbiting stars. Gravity also sets the stage for planetary evolution. It determines how much heat a planet retains, how long it remains geologically active, and whether it can hold onto an atmosphere. Too little gravity, and a planet becomes a frozen, airless rock. Too much, and it may become a crushing, hostile world. In this sense, gravity acts as a filter, shaping which planets can sustain complex chemistry and, potentially, life. The solar system is not merely a collection of objects held together by force. It is a long-term gravitational negotiation, one that has been unfolding since its formation and will continue far into the future. Beyond planets, gravity governs the lives of stars themselves. Stars form when gravity pulls together clouds of gas and dust, compressing them until nuclear fusion ignites at their cores. Once fusion begins, a delicate balance emerges. Gravity pulls inward, while the energy released by fusion pushes outward. A star is not a static object, but a dynamic equilibrium between collapse and expansion. The mass of a star determines its fate because gravity's strength scales with mass. Small stars burn slowly, conserving their fuel for trillions of years. Massive stars burn quickly, living fast and dying young. When a massive star exhausts its nuclear fuel, gravity wins decisively. The core collapses, triggering a supernova explosion that briefly outshines entire galaxies. In those final moments, gravity drives matter into extreme states, forging heavy elements that are scattered into space. The calcium in your bones, the iron in your blood, and the gold in jewelry were all created in environments shaped by gravitational collapse. Gravity is not just destructive here, it is creative, enabling the chemical complexity necessary for planets and life. The remnants of these stellar deaths are among the strangest objects in the universe. Neutron stars compress more mass than the Sun into a sphere only a few kilometers across. Their gravity is so intense that atomic nuclei are crushed together, forming matter unlike anything found on Earth. Space and time around them are severely warped, and their rotation can be so rapid that a city-sized object spins hundreds of times per second. These stars test gravity in a regime far beyond everyday experience, yet they obey the same underlying principles. Push gravity further still, and black holes emerge, as we have seen. But black holes do not exist in isolation. On galactic scales, gravity organizes stars, gas, and dark matter into vast rotating systems. Galaxies are not rigid structures, they are gravitational ecosystems. Stars orbit within them, gas flows through spiral arms, and dark matter halos provide the invisible mass that holds everything together. At the centers of most large galaxies lie supermassive black holes, whose masses can exceed billions of suns. These central black holes do not dominate the galaxy's gravity in the way popular imagination suggests, but they play a crucial regulatory role. As gas falls inward, it heats up and emits enormous energy, influencing star formation across the galaxy. Gravity here acts indirectly, shaping feedback loops that determine how galaxies grow and evolve. Galaxies themselves are not solitary. Gravity draws them into groups and clusters, bound together by immense dark matter structures. When galaxies pass close to one another, tidal forces distort their shapes, triggering bursts of star formation and reshaping their internal dynamics. Over time, galaxies merge, combining their stars, gas, and central black holes into larger systems. These mergers are not rare accidents. They are a natural consequence of gravity operating on cosmic scales. The universe we see today is the product of countless mergers layered upon one another across billions of years. On the largest scales of all, gravity reveals a pattern that is both elegant and eerie. Matter in the universe is not distributed randomly. It forms a vast cosmic web of filaments and voids. Galaxies trace these filaments, clustering where they intersect and leaving enormous empty regions between them. This structure emerged from tiny density variations in the early universe, amplified by gravity over cosmic time. Dark matter played a central role, collapsing first and guiding the flow of ordinary matter. The result is a universe that resembles a three-dimensional network, stretching across hundreds of millions of light years. Gravity is the architect of this structure, shaping the universe into a hierarchy of forms, from planets to stars, to galaxies to clusters and beyond. What is remarkable is not just the scale of this architecture, but its continuity. The same gravitational principles apply at every level. There is no boundary where gravity suddenly changes character. The equations that describe spacetime curvature near Earth also describe the motion of galaxies across the universe. Differences in outcome arise not from different laws, but from different initial conditions and scales. This universality is one of gravity's most profound features. It suggests that the universe is not a patchwork of disconnected phenomena, but a coherent whole governed by a small number of deep principles. Gravity across scales also reveals a subtle lesson about time. On Earth, gravity shapes processes that unfold over seconds, years, and millions of years. In stars, it governs lifetimes spanning billions of years. In galaxies and cosmic structures, gravity operates over timescales comparable to the age of the universe itself. Human intuition struggles with such vast ranges, but gravity does not. It works patiently, steadily, indifferent to the speed of human perception. Mountains rise and erode. Stars ignite and die. Galaxies collide and merge. All of it unfolds according to the same underlying geometry of spacetime. Seen from this perspective, gravity is not merely a physical interaction. It is a unifying narrative principle. It connects the solidity of the ground beneath us to the distant glow of galaxies. It explains why planets form, why stars shine, why structures emerge from chaos. And yet, it does all of this without intention or direction. Gravity does not aim. It responds. Matter curves spacetime. Spacetime guides matter, and complexity emerges from that feedback. This is both humbling and astonishing. It means that the richness of the universe arises not from elaborate rules, but from simple principles applied consistently across scales. At the same time, gravity's reach across scales highlights the limits of our understanding. We can describe how gravity shapes Earth and galaxies with remarkable accuracy. But we still do not know why gravity exists at all, why it has the strength it does, or how it fits into a deeper quantum framework. The same force that gives us mountains and stars also leads us to singularities and paradoxes. Gravity across scales is therefore both a triumph and a challenge. It shows us how much we have learned and how much remains unknown. To follow gravity from Earth to the cosmic web is to trace a path from the familiar to the sublime. It reminds us that we are not separate from the universe we study. We are embedded within it, shaped by the same curvature that governs galaxies and black holes. Every breath, every step, every orbit is part of a larger gravitational story, one that began long before humans existed and will continue long after we are gone. In understanding gravity across scales, we glimpse a rare continuity in nature, a single principle, quietly at work everywhere, weaving the small and the vast into a single, unfolding cosmos. That continuity invites a deeper reflection. Gravity does not merely arrange matter into structures, it sets the tempo at which the universe unfolds. On Earth, gravity gives us a sense of down and up, of stability and resistance. It anchors rivers to valleys, roots to soil, and bodies to the ground. These experiences feel local and immediate, but they are expressions of the same spacetime curvature that governs planetary motion and galactic evolution. Gravity quietly synchronizes processes across scales, allowing complexity to persist long enough for patterns to form, break apart, and reform again. Without this steady influence, the universe would be either too chaotic or too diffuse to support structure of any kind. Consider how fragile this balance truly is. If gravity were slightly stronger, stars would burn through their fuel too quickly, collapsing before planetary systems could stabilize. If it were slightly weaker, gas clouds might never collapse into stars at all. The universe would be dark, thin, and empty. Gravity's particular strength allows matter to clump just enough to ignite stars, form planets, and sustain long chains of cause and effect. It is not dramatic most of the time. It is permissive. It allows things to happen. In that sense, gravity is less like a command and more like a constraint, shaping what is possible without dictating outcomes. This becomes especially clear when we look at the role of gravity in shaping environments where life can emerge. On Earth, gravity helps regulate climate by maintaining atmospheric pressure and ocean circulation. It keeps water liquid at the surface, stabilizes axial tilt over long timescales through interactions with the Moon, and anchors ecosystems to a planetary surface. These conditions are not guaranteed by chemistry alone. They require a gravitational context that persists over billions of years. Gravity provides that long-term stability, acting as a quiet guardian of continuity. Zoom out again, and gravity's patience becomes even more apparent. Galaxies evolve slowly. Stars drift through spiral arms over hundreds of millions of years. Star formation rises and falls as gas is consumed, expelled, and recycled. Supermassive black holes grow over cosmic time, not by sudden consumption, but through gradual accretion and occasional mergers. Gravity rarely acts in sudden bursts. Its most transformative effects emerge through accumulation. Small tugs add up. Tiny asymmetries grow. Over time, order appears where none was intended. This is one of gravity's most counterintuitive qualities. It is simple in principle, yet endlessly creative in outcome. The cosmic web illustrates this creativity on the grandest scale. What began as nearly imperceptible density variations in the early universe evolved into filaments hundreds of millions of light-years long. Gravity amplified those variations, drawing matter along preferred paths, leaving vast voids between them. No blueprint dictated this structure. It emerged naturally from initial conditions and a single rule: matter curves spacetime. Spacetime guides matter. The resulting pattern is neither random nor designed. It is an emergent consequence of gravity applied consistently across an expanding universe. And within that web, smaller stories unfold. Galaxies form, merge, and transform. Star systems arise within galaxies. Planets form around stars. On at least one of those planets, matter becomes aware of itself and begins asking questions about gravity. That recursion is easy to overlook. The same force that binds atoms into planets also binds observers into the universe they observe. Gravity does not merely act on us, it enables us. It gives us weight, orientation, and a sense of place. It defines horizons, how far we can see, how far signals can travel, how long structures can endure. In a universe without gravity, there would be no stable vantage points from which to reflect on existence. Understanding gravity across scales also reframes how we think about our own significance. Human scales sit awkwardly between the microscopic and the cosmic. We are far larger than atoms, far smaller than planets, and vanishingly insignificant compared to galaxies. And yet, gravity treats all scales with the same indifference. It does not privilege the large over the small. It simply responds to mass and energy wherever they are. This impartiality is part of its power. It allows simple laws to generate immense diversity. It also means that meaning does not come from scale alone. The same gravitational principles that sculpt the cosmic web also hold your body together on Earth. There is no sharp boundary where the universe becomes abstract or irrelevant to daily life. The connection is continuous. At the same time, gravity across scales exposes the unfinished nature of our understanding. We can describe how gravity operates from Earth to galaxies with remarkable precision. We can simulate planetary systems, stellar evolution, and cosmic structure formation with extraordinary success. But we still do not know why gravity exists, why it has the strength it does, or how it fits into a deeper quantum description. The more we trace gravity's influence across scales, the clearer it becomes that description is not explanation. We know what gravity does. We do not know what it ultimately is. This gap does not diminish the achievement of modern physics. It defines its horizon. Gravity has guided us from the familiar to the sublime, from falling stones to colliding galaxies. It has revealed a universe that is coherent, structured, and astonishingly rich. And yet, it has also led us to questions that may not have simple answers. Perhaps gravity is fundamental. Perhaps it is emergent. Perhaps it is a shadow cast by deeper laws we have not yet discovered. For now, gravity remains both a guide and a mystery. It binds the universe together while pointing beyond itself. To follow gravity across scales is to recognize that the universe is not a collection of isolated phenomena, but a continuous process unfolding over time and space. We are part of that process, shaped by the same curvature that shapes stars and galaxies. In learning how gravity connects Earth to the cosmic web, we are not just learning about the universe. We are learning about our place within it. Seen this way, gravity becomes less about domination and more about relationship. It links objects not by forceful command, but by shared geometry. Nothing exists in isolation. Every mass subtly reshapes the spacetime around it, and every other mass responds. Even at human scales, this interconnectedness is real, though imperceptible. Your body bends spacetime. The effect is negligible, but it is not zero. In principle, everything influences everything else. The universe is not a collection of independent actors moving on a fixed stage. It is a single, coupled system where structure arises from mutual influence over time. This perspective dissolves the boundary between local and cosmic. The same gravitational logic that governs tectonic plates also governs the motion of galaxy clusters. The difference is not in kind, but in scale and patience. Gravity is slow. It rarely acts abruptly. Its power lies in persistence. Given enough time, even the smallest curvature leaves a mark. This slowness is why gravity is so effective at building large structures. Other forces dominate at short distances, but they average out over cosmic scales. Gravity never cancels. It accumulates. That is why it becomes the primary architect of the universe at large distances and long times. It is also why the universe has memory. Structures remember their past because gravity integrates history. The present configuration of galaxies encodes billions of years of gravitational interaction. In this sense, gravity is not just a physical law, it is a record keeper. The cosmic web is a fossil of early density fluctuations, preserved and amplified by gravity's steady hand. Even Earth bears such memory. Mountain ranges record collisions of tectonic plates. Sedimentary layers record ancient seas. Gravity pulls everything downward, but in doing so, it preserves traces of what came before. This memory extends to the stars. Stellar populations reveal the gravitational history of galaxies. Streams of stars trace past mergers. The motions of globular clusters hint at ancient interactions long since erased in visible structure. Gravity does not erase history, it writes it into motion. This is why studying gravity across scales is also a study of time. Gravity connects events separated by millions or billions of years into a single narrative. And within that narrative, emergence becomes possible. Simple initial conditions give rise to complexity, not because gravity plans it, but because gravity allows interactions to persist. Stability is the key. Planets remain in orbit long enough for chemistry to unfold. Stars shine long enough for heavy elements to accumulate. Galaxies remain bound long enough for ecosystems of stars to develop. Without gravity's stabilizing influence, nothing would last long enough to matter. This is an uncomfortable thought. It suggests that much of what we value, continuity, memory, evolution, depends on a force that is indifferent to meaning. Gravity does not care whether stars host life or galaxies host civilizations. It operates blindly, and yet, that blindness is precisely what makes it reliable. It does not fluctuate with context or intention. It simply follows geometry. In a universe governed by such impartial rules, meaning is not imposed from above. It emerges from within. That realization carries a quiet emotional weight. Gravity across scales reminds us that we are neither central nor accidental. We are the result of processes that had no foresight, yet produced conditions where reflection became possible. The same gravity that collapses stars and merges galaxies also keeps your feet on the ground as you stand and think about these things. There is no separation between the cosmic and the personal, only a difference in scale. At the largest scales, gravity may ultimately determine the fate of the universe itself. Galaxies bound together will continue to merge. Structures will simplify as expansion driven by dark energy stretches space ever faster. Over unimaginably long times, gravity's role will change. Locally, it will continue to bind what it can. Globally, it may lose the contest against expansion, leaving islands of matter isolated in an ever-darkening cosmos. Even then, gravity will not vanish. It will still govern what remains bound, still curve spacetime around surviving structures, still define horizons and limits. Gravity never truly switches off. It just changes context. Following gravity from Earth to galaxies therefore teaches a final lesson. Laws of nature do not exist for our convenience. They operate across domains we can barely imagine, on timescales that dwarf human history. And yet, those same laws apply here and now, shaping the ordinary world with the same consistency they apply to distant galaxies. To understand gravity across scales is to recognize a rare unity in nature. A single principle quietly governs the fall of rain, the drift of continents, the birth of stars, the dance of galaxies, and the architecture of the universe itself. We are not outside this process, observing it from a safe distance. We are embedded within it, carried along by curvature we rarely notice. Gravity does not announce itself with spectacle. It reveals itself through continuity. And in that continuity, from the solidity of Earth to the vastness of the cosmic web, we find one of the deepest connections between human experience and the structure of the universe. Following gravity across scales leads inevitably to a confrontation with time itself. Up close, gravity shapes landscapes and orbits. Far away, it organizes galaxies and the cosmic web. But threaded through all of this is a quieter, more unsettling influence. Gravity alters the passage of time. By the time we reach this point in the journey, time can no longer be treated as a universal backdrop. It is something that bends, stretches, and fractures depending on motion and gravity, and once time becomes flexible, questions about travel, destiny, and the ultimate fate of the universe stop being abstract science and begin to feel personal. One of the most famous illustrations of relativistic time is the twin paradox. Imagine identical twins. One remains on Earth. The other boards a spacecraft and travels at a speed close to that of light, journeys across space, then returns home. According to relativity, the traveling twin will age more slowly. When the twins reunite, one is older than the other. This is not a trick of perception or a flaw in clocks. It is a physical difference in experience time. The paradox arises only if we assume time must flow equally for everyone. Once we abandon that assumption, the result becomes unavoidable. Motion through space alters motion through time. Gravity adds another layer. A clock deeper in a gravitational field ticks more slowly than one farther away. Taken together, velocity and gravity mean that time is not shared equally across the universe. Every world, every orbit, every trajectory carries its own rhythm of aging. This realization has profound implications for travel beyond Earth. Interstellar distances are immense. Even the nearest stars are separated by years of travel at the speed of light, a limit that cannot be surpassed according to our current understanding. No engine, no matter how powerful, can accelerate a spacecraft past that barrier. At best, one might approach it asymptotically. Relativity offers a strange consolation. For travelers moving at extreme speeds, time slows dramatically. A journey that takes decades from Earth's perspective might feel like years or even months to those aboard the ship. In principle, a human could travel vast distances within a single lifetime, arriving in the distant future of the civilization they left behind. But this is not a loophole that allows easy exploration. The energy requirements are enormous. The dangers of radiation, collisions with interstellar dust, and the engineering challenges involved remain overwhelming. Interstellar travel is not forbidden by physics, but it is constrained by it in ways that make it profoundly difficult. Even if such travel were achieved, it would come with a cost: disconnection from home, from shared time, from continuity. You could cross the galaxy, but you would not return to the same world. Time would have carried everyone else far ahead. Gravity and relativity conspire to make the universe navigable in principle, but isolating in practice. These constraints become even more stark when we look beyond individual journeys to the fate of the universe itself. Cosmic expansion, driven by dark energy, is accelerating. Galaxies beyond our local group are receding faster and faster. Over time, this expansion will stretch space so much that distant galaxies will slip beyond our cosmic horizon. Light emitted from them will never reach us. The observable universe will shrink, not because objects are disappearing, but because space itself is expanding too quickly. Eventually, observers in our galaxy will see only their local cluster of stars. The evidence of the Big Bang, the cosmic microwave background, and the large-scale structure of the universe will fade from view. Knowledge of cosmic origins will become inaccessible, not because it was wrong, but because the universe changed. Looking far enough into the future, cosmologists predict a scenario known as heat death. As the universe expands, energy becomes increasingly spread out. Temperature differences even out. Stars burn through their fuel and fade into darkness. New star formation ceases as gas becomes too diffuse to collapse under gravity. Black holes slowly evaporate through Hawking radiation, leaving behind a thin bath of low-energy particles. Time continues, but nothing significant happens. No gradients remain to drive change. This is not an explosion or a dramatic end. It is a slow, quiet fading. The universe does not end with a bang, but with exhaustion. Gravity, once the great architect of structure, gradually loses its ability to gather matter against the pull of expansion. Bound systems like galaxies and solar systems persist for immense spans of time, but even they eventually decay. In this far future, time still flows, but meaning becomes harder to define. Without change, without structure, time loses its narrative quality. This vision of the future introduces a deeply existential theme: cosmic loneliness. As expansion accelerates, regions of the universe become causally disconnected. Communication across vast distances becomes impossible. Even light cannot bridge the gaps. Each gravitationally bound island of matter becomes a universe unto itself, surrounded by darkness. In such a cosmos, isolation is not a temporary condition, but a permanent one. There is no center, no gathering place, no cosmic conversation. Each surviving structure exists alone, carrying the memory of a once-connected universe. This loneliness is not emotional in the human sense, but it resonates with human experience in unsettling ways. It suggests that connection, like structure, is contingent and fragile. Gravity brought matter together, allowed complexity to emerge, and then, over time, yields to expansion that pulls everything apart. From this perspective, existence is a temporary alignment of conditions, a brief window where distance, time, and energy allow interaction. That window is precious precisely because it is finite. And yet, there is another way to read this story. The fact that time dilates, that journeys through space alter aging, that gravity shapes destiny across scales, means that the universe is not a static backdrop, but an evolving process. We are not trapped in a single universal timeline. Each path through spacetime carries its own experience of duration. The future is not something that happens uniformly to everyone at once. It unfolds locally, relationally. Even cosmic fate is not experienced all at once. Different regions age at different rates, follow different trajectories, and encounter different endings. The heat death of the universe is a global description, not a lived moment. This reframing matters. It suggests that meaning does not have to be universal or eternal to be real. Stars shine for a time. Civilizations rise and fall. Consciousness flickers briefly against a vast backdrop. Gravity makes these things possible by allowing structure and stability, even if only temporarily. Time dilation and cosmic expansion do not erase significance. They contextualize it. They remind us that permanence was never guaranteed. In fact, it was never part of the design. When we talk about the fate of the universe, we are not predicting an event that will happen to us. We are tracing a trajectory far beyond any human horizon. What matters more is that we exist during a phase when the universe is richly structured, when gravity still gathers matter into stars, when information can flow, when questions can be asked. This is not a trivial fact. It is a rare alignment in cosmic history. Gravity, time, and expansion have conspired to produce a universe that can reflect on itself, at least for a while. From this vantage point, the limits on travel, the inevitability of aging, and the loneliness of the far future do not diminish the present. They sharpen it. They tell us that the connections we have, the knowledge we build, and the meanings we construct exist within a finite window carved out by physical law. Gravity does not promise eternity. It offers opportunity. Time does not guarantee permanence. It allows experience. To understand time, travel, and cosmic fate through the lens of gravity is to accept a universe that is indifferent, yet astonishingly permissive. It does not care that we exist, but it allows us to exist. It does not preserve meaning forever, but it gives rise to moments where meaning is possible. In that sense, the story of gravity across scales leads naturally to an existential reflection. We are travelers through space-time, bound by limits, shaped by curvature, carried forward by time that does not flow the same for everyone. The universe will move on, expanding and cooling, long after our species is gone. But for now, we are here, embedded in a gravitational story billions of years in the making. And that, perhaps, is enough. When all the equations fall silent, when the simulations end and the graphs flatten into lines, gravity remains. Not as a number or a formula, but as a quiet presence woven into everything that exists. It is easy to think of gravity as something that restricts us, something that pulls us down, binds us to planets, limits how far we can go. But seen through the long arc of the universe, gravity is not a constraint. It is a condition for meaning. Without gravity, nothing would last long enough to matter. No stars would burn steadily. No planets would settle into stable paths. No chemistry would persist long enough to become biology, and no biology would persist long enough to become thought. Gravity is the reason structure exists at all. It gathers, it stabilizes, it allows complexity to arise and endure. In that sense, gravity is not an obstacle to freedom. It is the reason freedom ever appears. We often speak of ourselves as small in the universe, and in terms of size, that is undeniably true. But gravity tells a subtler story. Every atom in your body was forged in stars that lived and died under gravitational collapse. The carbon in your cells, the oxygen you breathe, the iron in your blood were all shaped by gravity's long patience. You are not merely in the universe, you are made of it. Stardust is not a metaphor meant to comfort. It is a literal statement about origin. Gravity assembled the raw material, held stars together long enough for fusion to occur, and scattered their remains across space so that new worlds could form. You exist because gravity once crushed matter to the brink of destruction and then released it back into the cosmos. That same gravity now holds you gently to the surface of a planet, allowing you to rest, to breathe, to sleep. There is a quiet symmetry in that. At a deeper level, gravity also reshapes how we think about motion and effort. We are taught, intuitively, that gravity pulls things downward, that falling is a kind of failure, a surrender to force. General relativity dissolves that picture. You are not pulled down. You're following a geodesic, the straightest possible path through curved space-time. The ground pushes up on you, preventing you from continuing along that natural trajectory. This reversal is subtle, but profound. It tells us that what feels like resistance is often support, and what feels like effortlessness can be the truest expression of natural motion. The universe does not force objects to fall. It curves the stage, and objects move accordingly. That insight extends beyond physics. It suggests that many of the paths we follow in life are not imposed from above, but emerge from the shape of the world we inhabit. We move along curves carved by history, environment, and connection. Understanding those curves does not remove agency. It deepens it. Gravity also teaches humility without despair. It shows us a universe that does not revolve around human concerns, yet produces beings capable of concern. It does not guarantee permanence, yet allows moments of extraordinary richness. Knowledge itself is one of those moments. To understand gravity is to participate in a tradition that stretches back through generations of thinkers who refuse to accept appearances at face value. From wondering why apples fall to imaging black holes at the centers of galaxies, the pursuit of understanding has been an act of quiet defiance against ignorance and complacency. Knowledge does not change the universe's ultimate fate. It does not halt expansion or prevent the long cooling of the cosmos, but it changes our relationship to existence. It turns confusion into clarity, fear into curiosity, and isolation into connection across time. Every insight is a bridge between minds separated by centuries, united by a shared desire to know what is real. In that sense, knowledge has intrinsic value, regardless of outcome. Gravity, perhaps more than any other concept, embodies this value. It began as the most ordinary of experiences, the reason things fall and bodies have weight. It led us to rethink space and time, to discover that the universe is dynamic, expanding, and filled with invisible structure. It forced us to confront limits on speed, on travel, on certainty. And yet, it also revealed a deep coherence, a single principle connecting Earth, stars, galaxies, and the cosmic web. Gravity is not just a subject we study. It is a thread that runs through the story of how we came to understand ourselves as part of a larger whole. There is something deeply calming in this realization. In a universe governed by curved spacetime and finite horizons, meaning does not come from eternity or centrality. It comes from participation, from being part of a process that began long before us and will continue long after. Gravity does not promise that we will be remembered forever. It does not preserve civilizations or protect stars from fading. What it offers instead is a window, a span of time where structure exists, where questions can be asked, where awareness can arise. That window is brief on cosmic scales, but it is vast on human ones. To exist within it is not trivial. It is rare. As you rest with these ideas, perhaps drifting toward sleep, gravity continues its work. It holds the planet together. It keeps the atmosphere wrapped around you. It guides the moon in its orbit and the Earth around the sun. Far beyond, it binds galaxies even as the universe expands between them. You are carried by curves you cannot see, moving through spacetime without effort, following paths shaped by mass and energy billions of years ago. Nothing is demanding that you be anything more than you are in this moment. You are not fighting gravity. You are moving with it. In the end, gravity does not give us answers to every question. It gives us something quieter, and in many ways, more profound. A sense of belonging to a universe that is structured, intelligible, and deeply interconnected. You are not separate from that structure. You are one of its expressions, and for as long as you exist, following your own gentle geodesic through time, that is enough.